So let's consider this new problem based on flywheel and turning moment diagram. A shaft fitted with a flywheel rotates at 250 rpm and drives a machine. The torque of the machine varies in a cyclic manner over a period of 3 revolutions. The torque rises from 750 Newton meter to 3000 Newton meter uniformly during half revolutions and remains constant for following revolutions. If then following revolutions, it then falls uniformly to 750 Newton meter during the next half revolution and remains constant for one revolution. The cycle being repeated thereafter. So the turning moment diagram for a shaft with the flywheel of 250 rpm is mounted. So the speed of flywheel is 250 rpm. So definitely this is the mean speed of the flywheel. The torque of the machine varies in a cyclic manner, a period of 3 revolutions. So for the period of 3 revolutions, we have to draw the turning moment diagram for 3 revolutions. I will draw the turning moment diagram, will not show the direct turning moment diagram for this problem. So we have to mark the lines for 3 revolutions. Make lines. Line. I will take for 3 revolutions. Just copy and paste it here, paste it here, paste it here. Okay. This first revolution. It is the second revolution, and this is the third revolution. Okay. Now the torque of the machine varies in a cyclic manner over 3 period of 3 revolutions. The torque rises from 750 Newton to 3000 Newton meter uniformly during first half revolution. Okay. So in half revolution, that means approximately here at the midpoint of this, the first half revolution. In this first half revolution, the torque increases from 750 Newton to 3000 Newton meter and then remains constant for the following revolution. Okay. Then falls uniformly from 750 Newton meter during the next half revolution and remains constant for one revolution. Okay. First we will rise this line again. First we will take the one complete revolution, and after this one complete revolution, it changes its value like this again at 750 and remains constant for the next revolution. So this first line represents the first one half revolution, and this represents blue line represents the one revolution, and this is again your half revolution, and this is your one revolution. In this manner, a cycle of 3 revolutions is completed. The value of torque at this point is 750 and the value of torque at this point is 3000. The value of torque at this point is 750 Newton meter and here value of torque is 3000. Okay, now first we have to determine the value of average torque. The given data for flywheel is mass and radius of gyration. Mass of flywheel is 500 kg and radius of gyration is 600 mm, that is 0.6 meters. 600 mm, that is 0.6. If I convert the speed in radian per second, so omega is equals to 2 pi n by 60. If I substitute the value of n as 250 rpm, which is given here, then we get the value of omega as 26.2 radians per second. Now, the period of overall cycle, time period, equals to 3 revolutions, that is 6 pi radians. 6 pi radians. Now, the total work done during this cycle, if I start my diagram from here, this is the starting point A, B, this is C, D, this point is A to B, gradual increment in the torque, B to C, the constant torque, C to D is gradual decrement in the value of torque, and D to E is again constant. And again, the cycle will start repetition of itself for the next 3 revolutions. Now, first of all, the area of T theta diagram, T torque and this is theta crank angle, shows the net work done during the cycle. So, net remember, the complete cycle has 3 revolutions. So here the cycle is not of 1 revolution, the cycle is of 3 revolutions. So net work done equals to the area under this curve A, B, C, D. If I name this bottom points, this is the pi 0° angle. This is half is pi. This is 2 pi, 3 pi, 4 pi, 5 pi, this is 6 pi. So area under this area of this trapezium, area of this rectangle, area of this trapezium, area of this rectangle. Okay, so the total area is this origin is O, this is O, A, B, C, D, E, and say this point is area O, A, B, C, D, E, F, and O. Say the complete area represents B. So you can calculate the area of this figure. You can write here that area under O, A, D, E, F plus area of this trapezium A, B, C, D, A. This is the total area. And area of this rectangle is 750 into 6 pi, and area of trapezium is the average of these two sides. BC length has 2 pi and this AD length has 4 pi. 2 pi plus 4 pi divided by 2, the average of parallel sides, into the distance between these two parallel sides, that is 3000 minus 750. So this is the area of the trapezium. Okay, now I will calculate this. Finally, value of this area, total work done during the cycle, is 11,250 by newtons meter. See, now the mean torque now the mean resisting torque, that is the torque which creates the same amount of work is done by the cycle. So T mean into period of cycle, that is 6 pi, equals to, should be equal to W. T mean is equals to 11 250 pi divided by 6 pi, and after dividing this value we'll get the torque value as 1875 Newton meters. So power required to drive definitely which overcome this mean torque, that is 2 pi nt mean by 60. So or T mean into omega, value of omega we calculated as 26.2 radian per second. You can also write here the value of n and T mean, and after calculating these two values we get the power is 49.125 kilowatt. So this is the calculations of power which is needed in the problem. We'll keep it as an answer. Of course. Now this is the mean torque, and I will draw this mean torque on this torque diagram. 1875 red line, 1500 approximately here. So red line represents mean torque. Okay, now the second problem is the finding of the coefficient of fluctuation of energy. And this coefficient of fluctuation of energy can be determined by the calculations as we did previously. The fluctuation of energy, first we will determine the value of fluctuation of energy. Now to determine the value of coefficient of fluctuation of energy, we know that the area above the mean torque line represents coefficient of fluctuation of this area represents. So on next page we'll write now coefficient of fluctuation of energy, that is delta E, is area above mean torque line. The area above mean torque. Now the area above the mean torque line, that is the area above mean torque line here, this area. And this area is area trapped within these lines. Say this point is L, this point is M, this point is P, point is Q. So area of this triangle LBP, area of this rectangle PQBC, and area of this triangle QMC gives you the maximum fluctuation of energy. We'll write here as the area L, B, C, M, completing the loop. Okay, is also equal to the area of triangle LBP plus area of triangle CQM, CQM, and plus area of rectangle PCQP, PCQP. Now these areas you can easily determine. Value of this base length LP and this height. This height is basically, this value is 1875. So this height is 3000 minus 1875, and this width you can easily determine by considering these two triangles. This LP, you can see that these two triangles are similar triangles. The area of LBP is equal to the area of CQM, 2 times of area of triangle LBP plus area of BCQP. I'm writing this because area LBP is equal to the area of triangle CQM. Okay, now I don't have a space here, so you can write these two. On next page here, this is the coefficient of fluctuation of energy. So area 1 by 2, area of triangle into 2 times is here. So base length is LP and height is BP. LP and height is P plus area of rectangle PQBC. So width PQ and height BP. BP into PQ, BP into PQ. BP is common in both, 2 times is cancel out here. BP into LP plus and you can find that this area value, the LP, calculations of LP. I will also show you how to determine the value of LP for LP. You know that this is our triangle LP. Okay, and this LP length, this point A, L, B, P, and I will take here point as R. I can make two triangles. Here it's A, here is R, and this base AR is equal to this pi radians length. The base length is pi radians, this pi. Here it is 750, here is it is 875, and here it is 3000. So you can write the height of the triangle ABR as 3000 minus 750 equals to 2250, and the height of this small triangle PB is as 3000 minus 1875 equals to 5 2 1 1. Okay, correct? Yes, correct. Sum of these two values equals to, and you know the value of this, want to know the value. So if these are two similar triangles, you can write here that ratio of LP to the AR is equals to ratio of chota wala, that is BP, small triangle, and the bada wala, that is PBR. LP is equals to BP. BP is your 1125, BR is your 2250, and AR is pi. Okay, value of LP 0.55. Similarly, you can find the value of next triangle base, that is the QM, and you will find that this QM is also 0.5 times of pi, and this height is also equal. Therefore, I wrote here that the area of this LBB is equal to the area of QCM by symmetry, and I multiplied by 2 times. So if I calculate the complete area above the mean line, that gives me the fluctuation of maximum energy, and this area finally comes as 887 Newton meter. Okay, so delta E value is equal to this 8837 Newton per Newton meter. Now we also know that delta E is equals to mk square omega square cs, and we have to find the value of cs. So 8837 divided by m, which is the mass, which is 500 kg, into k, that is 0.6 in meters square. Omega is 26.2 in radian per second square, and if you calculate the value here, that is 0.071 in fractions. In percentage, it is 7.1%. So in this manner, we can solve the problems based on the turning moment diagram as well as for the flywheel. If you have any doubt or query related to this topic or in this subject, then share your doubts or queries on the given numbers here. Okay, thank you.